Um, Project 4, hopefully you've all gotten at least a decent amount of progress made on. It's due, I believe, a week from today, if I'm remembering right. Um, Perhaps you guys are more aware of that than I am. There are a number of kind of common questions that have come up that I want to go over today to hopefully clarify things, maybe cut down the number of instances of those questions that keep reappearing. So some is just kind of background, how C works kind of stuff. It's not super specific to this project. Some of the later stuff we'll get onto is much more specific. So in terms of like data declarations, header files, C files, structs, that kind of stuff, it seems like there's a fair amount of uncertainty about what goes where sort of things. So how the model works in C, like a few weeks ago, or one of the earlier discussions actually, we went over how like pre-processing happens and whatnot, and how, when you say include some file foo.h, that just kind of pastes in the contents of that file as if it had been typed out literally in this file. So what that's used for is giving you sort of broad shared declarations that are common to your, well, not necessarily your whole code base, but that are used across multiple files. So if you have, some function that's written in one file, you have a declaration of that function in a corresponding header file, so that other code that wants to call that function can see what its type is. So when you compile that other file, you can do type checking and make sure you're passing, an int where it expects an int and a pointer where it expects a pointer and that sort of thing. If you don't have that declaration in scope that you pulled in via some include statement like that, you have potential for like type mismatches and so forth, or hopefully your compiler is smart enough to warn you about that you're calling a function that doesn't have a declaration visible. How that comes into play here, at least as most people have run into it, is with your like struct declarations for your spin locks. So in your header file, this file I'm working on here is itself, at least named as a header file. What you'll typically do with, a struct declaration, if you have some struct spin lock that you want to be able to use, is you put just a declaration of the struct type itself. You don't instantiate any, instances of the spin lock struct. You just lay out what its members are, so that when some other code, some other .c file that wants to use a spin lock includes this header file, the compiler when the compiler compiles that other C file, it knows what the contents of a spin lock struct are. But you don't want to have declarations that actually create a spin lock in a header file, because that sort of determines where that data lives, so to speak. And data declarations should pretty much always live in a .c file. So you'll have, a struct declaration with whatever contents. What you don't want to do is, struct spin lock my lock, because that's going to essentially kind of create a new instance of this struct spin lock named my lock in every C file that you then include this header file into, which is not what you want. If you do have a common data declaration, if you've got some variable, some global declared in a C file that you want to share amongst other C files, then what you need to do is put extern in front of it. That makes it not an instantiation of that type. It doesn't actually, reserve space for where that variable lives. It just sort of tells the compiler, yes, there is somewhere an instance of this struct spin lock called my lock. It'll be in some other .c file, and the linker will take care of, figuring out its address and resolving the references to it. But you don't end up with another separate copy of it in each C file you compile. So for this project, you'll want to have in like user.h, that's, kind of the common file where all your user library stuff is declared. That's where you'll want to put your struct spin lock and corresponding things, the declarations of your, spin init, spin lock, spin unlock, and the corresponding functions for mutexes and convers and semaphores, so that all the other user code that then includes, user.h gets those declarations, but doesn't end up, with redundant copies of everything all over the place if you would, put some global variable declaration in that .h file. So another, kind of following on from that thing that people have often been asking about is how to initialize things. If you've got, some user library file, there's one in particular that hopefully you've, found if you've done part 2 here, where you've got some global variables that are potentially accessed by multiple threads if they call into the functions in that file concurrently. And you need to, add some locking so that those accesses to those shared variables in that file are synchronized and not going to be racing with each other and doing concurrent updates that are going to lead to bugs. So if you have some, I didn't type that file name right, but it doesn't matter. If you have a .c file with some global variable and a function that accesses it, and you want to make this thread safe by adding, locking around it. So you have, say, spin lock, some lock, and then an unlock after it. You'll need to, of course, declare your spin lock. So you have, a struct spin lock like that. But then if you don't have some existing function that's called at the beginning, this raises the question of how you initialize some lock there. Because we have this spin init function that, is the sort of designated way to initialize your spin lock, but what do you call it from? This is not an init function foo here, this is just some general purpose function that might be called repeatedly at any time. So you have a couple options. One is, in some cases, it's not unreasonable to add some sort of initialization function that whatever code that is going to be using this code is going to need to call to kind of set up, initialize the state of the data in this file so that it can then use it. For this case in this project, that's actually kind of not the best way to go about it. It would be a little excessively cumbersome. So what's more advisable is just to kind of statically initialize this. You can, initialize a struct with a static initializer the same way, you can say, if I wanted to initialize this to 3, I can do that. You can do similar with a struct, and you can just say which member is what, like so, and set it up however you need it to be. So you can, initialize it statically so that it's just by default going to be, going to have whatever state you put here without having to explicitly call some code when your program starts running. Yeah. For this specific syntax that I've used here, yeah, if I take that out, that's going to be a syntax error. I'm pretty sure I actually tried compiling this, but so take that all with a grain of salt, but I'm pretty sure that's the case. What you can do equivalently, it's a little more error prone and fragile, but it's a bit also more concise. If you know exactly what the order of the members of your struct are, you can leave off these. These are called designated initializers for what it's worth, sort of obscure sync terminology. But you can just say that, and that's going to do exactly the same thing. But usually making it explicit like that is, preferable. It's more readable. It's, harder to screw up. So I would recommend this way. So that, obviates the need for having to call spin init to set, these various members of your struct to whatever values are appropriate for, your initialized unlocked spin lock. Any questions on that so far? Okay. So another common point of confusion, double pointers and out parameters in C functions. Or in this particular case, the double pointer. Out parameters are not always double pointers. If you're wondering what the heck I'm talking about, this comes down to the fact that in C, a function declaration can only return one thing. Sorry, can we keep it a little quiet over there? Thanks. A function, a given function only has a single return type. This returns int, and it has, some parameter, string, say. But if I want, in effect, a function to return multiple things, I can't just say, this returns an int and a char. That, a syntax error, so it doesn't support that. So what's typically done is, well, depending on the context, you can return like a pointer to a struct that you allocate or something, but that involves memory allocation, so it's a little perhaps excessively complicated for many situations. What's typically done is what's called an out parameter. It's you add a parameter to your function that's used just kind of as an output area rather than providing data to the function. It'll always be a pointer, and it provides that function a location in memory where it can, in effect, kind of return additional stuff. So if in addition to an int, if this is going to return, some value, I also want to give back to the calling code, I don't know, a long. I'll pass in a pointer to a long, say like that, and before returning, I'll just dereference that pointer and set it to some whatever value I'm looking to, kind of return as an auxiliary piece of data to the actual literal return value of this. So that, gives you a way to add, to your C functions kind of additional channels by which you can pass data back to the calling function without, or working around this restriction of the fact that you can only really return one thing. So how this relates to Project 4 is specifically the declaration or the signature of, why isn't this working? Come on. Well, that's not helpful. In any case, the join function, or the join syscall rather, returns an int, which is, it tells you the PID of the thread that had exited and that you've now collected. But it also has this double pointer ustack, which sort of corresponds to, with clone, you have that function pointer argument, you have the void argument to pass to it, and then you have a void pointer ustack, like so. You'll note that this is a void pointer, whereas this is a pointer to a void pointer. So what's going on here is that this is an out parameter. So the join wants to kind of return two things, but it's already returning an int as its kind of main return value to give you the PID back. What the signature is designed to do is to allow it to also hand back the value of the ustack pointer that was passed in when the thread that has now exited was created. So you pass, instead of a void pointer, you pass a pointer to a void pointer, and then join will dereference that and write in that location in memory this value that it initially got in the clone call that created that function. So it's writing a void pointer, a memory address to memory, because this is, again, a double pointer. It's a pointer to a pointer. So you might be also wondering why this is necessary. It's not actually strictly necessary to give back the ustack pointer to the thread that calls clone. It's just sort of a convenience thing to make the user space implementation a little simpler. Basically, what this amounts to is when you create a thread, you need to pass in some chunk of memory for its stack, and you need to allocate that beforehand. It's user space's responsibility to allocate memory for the new thread stack before it goes and creates that thread, so it has a stack to work with. So it'll allocate that memory, and then once the thread exits, you want to also be able to free that memory so you don't accumulate these giant buffers that you're using for stack space for all your threads. If you have some long-lived program that's creating one thread and another, and they're have lots of short-lived threads, say. So to avoid leaking all that memory, you want to free it when you call your thread join function, because you know that thread is exited, it's not using its stack anymore, nothing else is going to need to use that stack, so you can recycle that memory. So in order to be able to do that, you need to know the value of the pointer to pass to free, or whatever, the converse of whatever memory allocation operation you used. So you could, maintain a data structure in user space, mapping PIDs to stack, not stack pointers in the sense of like your ESP register stack pointer, but pointers to the buffer of memory that you're using as your stack. You could, keep track of that, and then when join returned whatever PID, look up the corresponding stack buffer for that thread's PID and free that. but it's a bit of extra work, and so it's a little simpler, at least for the purposes of this project, to just stash that original value in the kernel, have it keep track of that for you, because it's already got this proc struct where it's stashing a bunch of other information about every running task in the system. So you can just kind of sort of have the kernel hold on to that for you and then hand it back when you go to collect that thread with the join call, so that you can then just free that memory without having to have some extra auxiliary data structure that you're doing all that extra accounting and bookkeeping in. So that's, as I said, not strictly necessary. If you were doing a more kind of serious real-world robust threading implementation, you probably wouldn't take this approach, but for our purposes, it kind of simplifies things. Questions there? What these uStack parameters mean? Hopefully that clears things up. All right. Now on to park and unpark. And set park being the kind of third little hanger on there. Those are, you will need, of course, corresponding functions in the kernel, as we saw in project 1, where you first implemented a system call. But they are system calls; they're not just functions. So you'll need to, do all the kind of plumbing work to, install entries in your syscall handler table and declare new constants that identify what number is reserved to indicate you're calling park rather than unpark, or instead of clone or join or whatever. You'll need to do all that. It's a little bit tedious, but there's not too much to do. You basically add your user declaration, an entry to the usys.s, pick a new constant number to identify it, add an entry to your syscall table, and add a sys underscore whatever function to retrieve its arguments. Same usual procedure you do with any other system call you're adding. What those system calls do is, I think, perhaps simpler than a lot of people appear to think. Some people have been asking questions, seem to be under the impression that there should be like queuing going on in the kernel with park and unpark. There should not be any queuing involved there. Those are really just much simpler kind of put a thread to sleep, wake it up, that's it. There's the slight complication of set park, which we'll get to in a moment. But it's not like calling park puts you on a queue of some set of threads that are waiting for something. You will need to implement that later for your convers and mutexes and semaphores and whatnot, but that's not going to be done in the kernel in the park implementation. That's going to be done in user space in your mutex and convert code. What park and unpark and set park provide you are the sort of simpler primitives from which you can build that. Starting with a simpler operation of just this thread calls park, so it's suspended and it's just paused, and that's that. It's not on any particular queue. It's just kind of sitting there waiting for some other thread to unpark it and wake it up. And then another thread can then use that other syscall, unpark, passing in a PID to identify exactly which particular individual thread it wants to wake up, and then set that thread running again. That's really all those syscalls do. Now there's the complication of set park, which isn't too huge a complication. It's, as you may recall from the textbook or when we talked about this in class, it's basically just a little workaround for a race condition that arises when you use just park and unpark in the sort of obvious intuitive way, which is that if you have, some flag, well, actually, I wonder if the Wi-Fi is working yet. That would be great. Yay. So in our textbook chapter here, I believe it was, nope. No, wrong chapter. Anyone happen to remember where this was? Should have looked at this beforehand. 28? Thank you. So yeah, if you use park and unpark in code like this, what you end up with here is a race at lines 21 and 22 here, where you want to put yourself to sleep and allow a thread to wake up, but also update memory for some little internal, spin lock here. Like this guard member here is just sort of an internal spin lock protecting the contents of this lock T struct here. But you have then this window of vulnerability to erase condition where if in between line 21 and 22, another thread sees that guard has now been set to 0, acquires that spin lock, does whatever work it's doing, and then releases the lock T lock, not just the flag spin lock, or sorry, the guard spin lock, and then sends an unpark signal before the first thread has even reached line 22 there, then you're going to miss your wake up signal, and the thread is then going to continue on park itself and just hang there because the unpark already happened and it missed it. So this is explained here. If you want to go over this in more detail, you can read this paragraph here, wake up waiting erase. But how we solve this is by adding in between those this set park call, which is just sort of a little state change in, it just sort of tells the kernel to make a little note about the state of this process. Basically that it is about to call park, but hasn't quite done so yet, because it needs to first do this little thing updating memory in user space before it actually makes that call to suspend itself. So what that state change that the kernel does indicates is basically just marking that if an unpark for this thread arrives before my next park call, ignore my next park call. So you solve that wake up race or the wake up wait problem where that situation I described a moment ago comes up, because if that unpark does arrive before you've gotten around to call park, if you've been careful and called this set park beforehand, then the kernel knows that, okay, the next park after this should be ignored. So you don't suspend yourself, you keep running as was actually kind of desired by the other thread that sent that unpark signal to wake you up. So it's basically just, set park, park, unpark are basically just sort of manipulating little bits of state. You probably may want to add some little variables to your proc struct to track exactly what scheduling state that task is in. You could alternately add new potential values to the existing state member of the proc struct, which we can look at here if in case people are wondering. Yeah, where'd it go? If we look at kernel proc.h, so we have this proc state here that is the existing representation of scheduler state that can be unused embryo, sleeping, running, etc. You could add values to that. I would actually recommend against that, because then you're going to have to figure out exactly how the new states that you add relate to the existing states and update a bunch of conditional checks in all the existing code and make sure you get all that exactly right, and that's probably going to be error prone. So it's probably easier to just add some members to the proc state to indicate, have you been parked, have you set parked, blah, 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 and use those to, add little conditional checks to do like the error checking that's described in the project description, such as, if you call set park twice without calling park, that doesn't make a whole lot of sense. You should only really be calling set park right before you call park. So if you get 2 set park calls in a row, the second one should fail because you've already called set park, and that's not a sensible thing to do. So you can use those little state variables to implement that checking. The queuing that happens, that some people erroneously thought was supposed to be happening in the kernel via park and unpark, that should all be managed in user space. You can, use the park unpark mechanism to maintain a queue in user space. Use a linked list or something with a node in that list per thread that's waiting for a mutex or waiting for a conver to be signaled or waiting for a semaphore to be posted or whatever, and just store like a PID, say, hint hint, in each node of exactly which thread is occupying that entry in the queue. You can keep it ordered, you can maintain fair FIFO ordering, wake things up with unpark by dequeuing an entry from the head of the list, the thing that's at the front of the queue, grabbing that PID, using unpark, and then they'll just wake up in that order because that's the order that user space is explicitly telling the kernel to wake things up in. The kernel doesn't need to maintain any sort of list or ordering. It just suspends the thread, wakes it up on unpark when user space has told it to wake up that specific thread. So the queuing all happens in your mutex, conveyor, or semaphore code. which again, you can, if you want, implement all three of those directly using setPark, park, and unpark. You also have the option of implementing some of them in terms of the other. Like some of the previous discussions looked at how you use a convar and a mutex or whatever to implement a semaphore. You can certainly take that approach if you want. Once you've implemented your mutex and convar, you can then implement your semaphore in terms of those rather than calling directly into setPark and park and unpark. Which of those you choose to implement in terms of which others is entirely up to you. Hopefully it's obvious that at least one of them must be implemented in terms of setPark and park and unpark, because if you implement all three of them in terms of each other, you will have infinite recursion, and that's not going to get you anywhere. So anyway, but you do have that option. However, it has occurred to me since writing the initial project description that in order to allow you to do that and still be able to kind of grade things flexibly and give partial credit where, if you get your convar right, even if you screw up your mutex, if your convar was implemented in terms of your mutex, you should still get credit for your convar, even if that, if that part was right, even if it was built on top of something that had a mistake in it. So in order to allow that to be graded, conveniently without having to like manually edit everyone's code, what I'm going to update the project description to have instructions to do is to take those three parts for part 4, your semaphore, your convar, your mutex, put each of them in a separate file, so that when we're grading, we can just replace things at file granularity. So your CV init, CV weight, CV signal should be in one file, cv.c. And then similarly for your mutex functions, similarly for your, semaphore functions, the declaration should all still be just in user.h, so that anything can just include user.h and have all those functions declared in necessary struct types. But the functions implementing them, put them in separate files so that the grading script can give you a known good implementation of a convar and a semaphore, and then check if your mutex works correctly given those. Similarly, give you a known good implementation of a semaphore and a mutex, and check if your convar works correctly, implemented in terms of those other things. So as I said, I'll post an update to the description and send out an email describing that in a bit more detail. It shouldn't be too invasive a change. You'll just need to add a few lines to your user makefile and split things into 3 files instead of 1. Let's see, any questions on that? Yeah. Totally fine. Yeah. You'll have similar primitives to work with. Referencing the textbook and basically just sort of following that example is okay. Yeah. Yeah.
So, like, should Park call a different system call in order to deschedule a thread?
It should not call any other system calls. So there are existing functions in the kernel that you will want to use to implement Park. If you look through proc.c, there's one in particular that will be the hopefully obvious choice. That actually, good that you mentioned that. That function has a slightly odd interface. Well, I will essentially kind of give away what it is by describing it. But it takes a lock that it unlocks. It's sort of like it's actually very analogous to the interface of the convar weight function. When you've got a convar, you've got your CV and you've got some lock that you're holding, and you call this convar weight function, and it will atomically release the lock and suspend you. And then when it returns, having been woken up by, for whatever event you were waiting for, it will have reacquired that lock. So that there's I'm pretty sure if I'm remembering right, I think I am, a very similar interface on this one function in proc.c that you will want to use to implement your park syscall. And then a corresponding function with a simpler interface doesn't have that, lock, release, reacquire complication that will be used on the wake up side in your unpark. But yeah, there is more to it than just setting state equals sleeping. You will need to, take some action, call a special function to suspend the thread, and then in park call another function that wakes it back up. Set park, on the other hand, is relatively simple. That should just be some little variable manipulations. Shouldn't require any, changing the actual scheduler state. It should be just kind of making a little note of basically this process called set park. Other questions? Okay, the other thing sort of in terms of hand-in code organization in order to allow more, well, ultimately better for you grading. If you do attempt the bonus, which I suspect may be significantly trickier on this one in most people's opinion than the last one, do hand that in as a separate thing. Create like xv6-bonus and hand in a different version of your code into that. The hand in slash p4 slash your username slash xv6 should be exactly as described in the non-bonus part of the description, so that when we're running the test scripts to test your code, the function signatures will match up. If you hand in your bonus code as your regular xv6 code, then there's going to be a mismatch in the signature of clone. So do that separately, and they'll be graded separately, so we won't have compile errors when you go to test your code. That also I will update the description page with and send out an email, but just to announce it early. Is anyone thinking they're going to do the bonus? Has anyone started work? I know at least one person has started working on it, but I don't think he's here. Yeah? Is that a yes? Maybe? All right. Yeah, it'll probably be tricky. It might not be obvious why there is quote-unquote some assembly required, but it's because, well, to give a little bit of a hint, if you don't, if you just call that version of the code straight from C, you will have two functions returning to the same point, two threads returning to the same point. It should be basically just like fork, rather, in that you no longer have you no longer have two, or you no longer have the two additional arguments to clone. So they're only differentiated by the return value of clone. You're not passing in the function pointer that tells it, where to start executing in the new thread. It's much more like clone in that they return to the same point. It's just what the return value is that differs between the two, that lets you distinguish the new thread from the old thread. And based on that, you will need to then dispatch to the function that you want the new thread to execute with the desired argument. But if you do that from C, you'll have a problem in that you'll basically have two threads trampling on the same stack. You could think, well, I can switch the stack in the systcall because I'm passing the stack in. But if you do that, you'll have a problem because you'll still, return to the same place, and that code, generated by the C compiler is going to expect the stack layout that it left on the stack there. And if you're suddenly returning to a new stack, that's not going to be there, so that's going to cause problems. So you'll need to write some assembly to, carefully arrange things to, the assembly will need to call the clone syscall and deal with the sort of delicate state that you end up with afterwards where you kind of have two threads temporarily running on the same stack. So you have to be very careful about what you touch and in what order. So anyway, there's the hint you'll get for the bonus. Questions? No? Okay. Okay, finally, a number of you have asked about tests for Project 4, which I was hoping to get out a little bit earlier than this, but hasn't happened yet. So we'll go over some options here. First, I'm going to switch to my implemented version of Project 4. And go to, let's see. So it's a little tricky to test just part 1 in isolation without essentially kind of giving code for part 2. Could be done, but it's kind of more effort than it's worth. So what I'm going to provide are some part 2 tests and some part 4 tests. The part 2 tests will include part 1. The part 4 tests will include part 3. Hopefully that's sufficient. For reasons we might have time to discuss here, it's actually a little tricky, again, for different reasons, to devise a test that reliably demonstrates just part 3, or at least a simple one. So let's see. So if we were to implement a test for part 2, well, let's just get our header files here. So we'll insert, say, echo.c, work out a copy of that, just so we have our headers there. We want a multi-threaded process, right? So we can just use a good example is inserting nodes to linked list. So we'll have that, and we'll have some value. We'll have a function to create a node with a given value. You'll say create a node, malloc its size, and val equals value, or value, and return n. And then we can have a thread function, which is going to take an argument that we're not actually going to use. We're going to have a head node, which is initially going to be null. The list is going to be empty. And what this is going to do is just, for some number of iterations, let's say count is 100, it's going to create a new node, with the given value and insert it by doing, n next equals head and head equals n. But as hopefully you recall from our concurrency section, this in and of itself is not sufficient. If we have this actually called from multiple threads, if we have, say, thread create with thread func, we're not going to bother with an argument, and then we have another thread doing the same thing, these two are going to be racing with each other when they go to do this insert. So what you'll also need is a spin lock that you may want to initialize somehow or other. But before we start messing around with the shared list head, we're going to lock it and then unlock it. If you're bothering to take pictures of the screen, no need. I'm going to send this out and post it later anyway. So that'll protect your shared state there, that global head node. So you should be able to run this code with arbitrarily many threads for arbitrarily large iteration counts and not lose any nodes. So you should be able to do this and then iterate over your list and verify that you have the expected number of nodes. There's also another subtlety here that gets into the library locking issue that is hinted at in part 2 that you'll need to solve with a bit more locking than just that. But hopefully you can figure out where that needs to go. So that's a simple test of your thread creation, your spin lock working, and the fact that you've made the necessary part of the user library code thread safe so that multiple threads can call into it. So if this isn't entirely finished, but something basically like that would be a decent test for part 2. So I'll fancy that up very slightly and post it hopefully later this evening. Questions there? It's pretty straightforward. Good chance you could have written something like this yourself, but it'll be provided. For part 4, that I have actually written in advance because it's a little more involved, but similar to this, reusing examples we've used in the past, you may be able to guess where part 4 is going. This test is a producer-consumer queue. Should look fairly familiar. There is a semaphore-based version here that I'm showing you that just uses your sem-wait, sem-post in kind of the usual manner to build a producer-consumer queue. Then has 2 threads. A producer thread that just iterates over some count and inserts integers into this producer-consumer queue. There is a slight little bit of extra functionality I built in where the program takes a command line argument that's a bit mask of 2 bits. It's somewhere between 0 and 3, as the usage message tells you there, if you've used it without an argument or with an argument that's out of range. What those 2 bits indicate is whether or not each thread should run kind of artificially slowed down. So you get that mode integer, it's just 0, 1, 2, 3. and it passes that in, cast to a void pointer. This is another little test here. This should work. If this should test how you're retrieving and passing along your syscall parameters, because while this may not look like it would be a valid pointer, it's just 0, 1, 2, or 3 that I've cast as a void pointer, it should still be allowed because the kernel does not need to dereference that value. It's basically just a string of bits that happens to be the size of a pointer that it passes along to the new thread function. So I'm, sort of munging that int into a pointer and passing it along without actually, it pointing to anything. And then the thread functions that receive that then, cast it back to an int and retrieve that mode value. What it then uses that for is it checks one bit of that mode. You see the consumer thread here checks with, ANDing it with 2, so it checks the upper of the 2 bits. The producer thread up here checks ANDing it with 1, so it's using the lower of the 2 bits. And if so, just sleeps. So you can use this to sort of test the timing so that if, you can just test that it works well when, the producer is slower than the consumer, or when the consumer is slower than the producer, or when they're both running full throttle, or they're both alternating between, sleeping and running. So with that in place, I will, let's see, do I have those? Yes, I do. So I'll just add those to my user make file here. Part 4 sem and part 4 CV. The part 4 CV is the exact same thing, just implemented instead of with semaphores using a pair of condition variables in the mutex. So basically the producer-consumer examples we looked at previously. So if I then go in, compile and run that, I should be able to do part 4 sem. If I don't pass an argument, it'll tell me that. So I'll do part 4 semaphore version with an argument of 2. It'll just spit out all those numbers because the consumer is just receiving them from the producer and printing them. If I do part 4 sem with a argument of 1, that means my producer is going to be sleeping. So you'll see it'll run kind of gradually slower and slower because it's sleeping for the length of time of the number that it's about or just enqueued. So it sort of gradually slows down, but eventually makes its way to the end. And there we go. If we run it similarly with 2, that'll be with a slow consumer and a fast producer, but you should see basically the same behavior there. The timing that you perceive in kind of real-world wall clock time might be a little funny because QEMU is not always super timing accurate, but it should be noticeably kind of slowing down as you run. Finally, at the value of 3, they'll both be slow. You don't actually notice this as being a whole lot slower than either of the 2 versions, mode 1 or mode 2, because now you have both threads, you do have both threads alternating between sleeping for a while and being active, producing or consuming, but those sleep periods are largely overlapped. So it doesn't actually slow down the overall execution a whole lot. So you should be able to run both versions of those, CV and semaphore, and see results pretty much like that. If you don't, you've got something to fix. As I said, I'll provide these in a download that I'll send out an email about. I think that's probably all the test programs you'll get, but hopefully that's sufficient. It should give you reasonable coverage. These tests will, of course, exercise your park on park, set park code. You may, of course, still want to do your own more intensive testing where you hammer on your code looking for race conditions more intensively. That would certainly be a good idea, but this should run you through the basics. Any questions on that? Or anything else? Okay, if not, that'll be all for today.